Hello everyone, welcome to Vectorly. Today we are going to solve work power energy problems from Pathfinder. Uh, Today's problems will be a bit basic level and some more conceptual questions are involved today, and in the upcoming parts you will encounter much more difficult questions. Okay, like this video, okay, subscribe our channel and do comment your suggestions. Okay, we will improve our video quality and all our question selections and all. First question: two identical ropes A and B of uniform mass per unit length are suspended from ceiling and are made to pass through a metallic tubular structure C as shown in the figure. The structure is made by welding two identical bent tubes. There is no friction between the ropes and the tubes, and the structure is almost inertialess. Initially, the structure is held at rest and then released. What will happen? Now, let me redraw this. Okay, let me redraw this over here. I have a pipe. This is that particular metallic pipe. Okay, now what happens is, let the total length be, I am assuming total length of rope. I'm considering single rope, which is L. Okay, this total length is L, and let this part be small l. Okay, and this part be X. Then what about this part? This is capital L minus X. Okay, now if you notice clearly, no matter from this end to this end, the total length remains constant, which is L minus L. Okay, which remains constant throughout the motion. Okay, let's suppose this is far below and this doesn't come totally outside. So this L minus L is completely, this is completely constant, correct? Now, if you see this particular, what do you call, rope is attached to this, that is a reference, that is a ground or the ceiling. Okay, let's suppose this is a ceiling. In that case, the velocity of this, the particles present in this part is, velocity is 0. Okay, now if this velocity is 0, this velocity is also supposed to be 0, else this constant L minus L constant length won't be satisfied, so velocity of this part is also 0. Now let's suppose, let this be the pipe. Okay, two pipes are welded together. Now that this pipe goes down, intuitively one can say it goes down with a velocity v. Okay, then the wire or the rope in this thing would also move downward with velocity v, correct? Okay, the wire will move downward with velocity v. Okay, also since it is moving downwards, okay, the length of this part, the part above, should increase with a velocity, same velocity v, right? Because this is constant, the topmost end is fixed, so this length should increase with same velocity v. The rate of change of length is v. That is not, this rope is not moving at this particular point. The rate of change of length is v. So for increasing that length, the wire should move along this pipe. So along this pipe, the wire moves, that is the thread moves along this pipe in this direction of velocity, with velocity v, and bottom with velocity v. So the net velocity would be v root 2. Okay, this is the net velocity acting here. Now there is no kinetic energy for this part and this part, there is only this is moving. Okay, Now what happens is, exactly, let me explain again why this is v in a different perspective. Let's suppose this is happening over here, and we are keeping this particular metallic thing as metallic pipe as frame of reference, then the whole system will move with the velocity v upwards, correct? So this thread will move, that is this rope will move with velocity v upwards, velocity v upwards, velocity v upwards. The velocity along the rope will be same, so this will move with the velocity v in this direction, correct? Okay, so this velocity v in this direction is justified. Okay, now the net velocity is v root 2 in this direction. Now let's use the concept of conservation of energy. Okay, now we are going to consider this part and this part separately, and this part as part 2 and this is part 1. Okay, this belongs to part 1. Now let's assume, okay, mass per unit length, mass per unit length of wire is nothing but mu. Okay, mu kg per meter or any other units. Okay, now the potential energy, initial potential energy is nothing but this total length is L minus L. So mechanical energy or total energy initial that I'm going to calculate. Initially, let's suppose it's at rest. Okay, now there is no velocity, and initial position let's mark. Okay, this is the initial position, and finally what would happen, this particular thing would go down, okay, by displace by a distance of x. Okay, now initial mechanical energy is, I'm taking this as a reference, so what I get is lambda into L minus L. This is the total mass of this part and this part into G. I'm calculating the potential energy where the center of mass will be at a distance of L minus L by 2. Okay, let's suppose L minus L by 2 is above. Okay, I'm taking L minus L by 2, that is L is greater than L. Okay, now else L minus L by 2 is greater than 0. I'm taking this condition. Plus this is the reference point, so potential energy of this part is 0 and this is massless, let's assume. Okay, this is the initial mechanical energy, and let's see whether it is released. Yeah, it is at rest initially. Now mechanical energy, that is final mechanical energy, is nothing but the same thing. This doesn't move. Okay, into L minus L by 2. Okay, this part doesn't move because the length of this part and this part gets adjusted. Okay, plus what is happening, this part goes down, so the potential energy of this part gets decreased. Okay, minus of lambda into this part is small l. Okay, small l g into the displacement x, and the kinetic energy is increasing, plus half. Okay, what is the mass of this part, lambda l. Okay, half m into v square, that is the total velocity is v root 2, correct? So v square into 2, this 2 gets cancelled. So what you get is this whole part should be 0 because initial mechanical energy and final mechanical energy should be 0 because this is the conservative forces are acting here. So lambda L into V square should be equal to lambda L into G into X. Okay, lambda L gets cancelled, so V square is nothing but Gx. Now if we differentiate again, 2V into dV by dt, which is acceleration, I am considering the velocity. Okay, acceleration let me take uh, equal to G into V dx by dt. So what I get is acceleration A is equal to G by 2, and it is acting downwards. Okay. Now X is C. Now if you see, X is nothing but downward motion, correct? So this acceleration A should be downward. So the whole system is moving with the, not whole system, this particular thing is moving with acceleration G by 2 downwards, that is 0.5 G. Okay, point C. Uh, so option C is correct. The rope will heat up. In this case, if the rope gets heated up, we can't directly equate these two because there is some loss of energy. Okay, so option C is the correct option. Question number 2. A slider is released from a point P on a frictionless track, which bends into a circular loop at its bottom. Height of the point P above the ground is selected such that the slider is just capable of moving round inside the circular loop without breaking contact anywhere. The circular loop is now made elliptical without altering its height. The slider is now released from a point Q, as shown in the figure. If the slider again rounds the complete elliptical loop, the minimum height of Q above the ground is. Okay. Now, first, the most prone point is at which the contact will break is, let's suppose, most prone point is the top, that is points of this and this is the most prone point where a particular slider may lose the contact. Okay, now let's take, when the slider is at that particular instant, the normal reaction would be acting in this direction and weight mg would be acting in this direction. Now the centripetal force or centrifugal force at this place, because the normal reaction will also try to push downwards, mg will try to push downwards, so centrifugal force will be acting here, which says mv square by radius of curvature at that particular position is nothing but mg, okay, plus n. Considering the minimum case where the normal reaction is 0, okay, we will consider the minimum case where the normal reaction is 0, limiting case, that is, okay, mv square by r should be equal to mg, and v is nothing but root over rg, that is velocity at this particular point should be root over rg. Now if you compare both of these, this height is same, so this is r and this is r, so the same 2r will be here, and here is also 2r, but around here it is less than 2r, correct? And if you draw an ellipse, in this ellipse, if you draw a circle around here, this would be a circle of minimal radius, not the radius r, so the radius is reduced. So velocity in, let this be case 1 and this be case 2, velocity at the topmost point, this is velocity at top, velocity at topmost point in first case is greater than velocity in topmost point at the second case, because the radius is small in the second case. Okay, so what we can conclude is kinetic energy at first case is greater than kinetic energy at second case. Since the total energy should be conserved in the second case, Q can be a bit lower than P, because we require less kinetic energy at this point, and the potential energy is both same. Potential energy at that particular point, that is topmost point in 1, is equal to potential energy at the topmost point at 2, but the kinetic energy is less, so let the total energy can be less. Since we are releasing it from rest, just the potential energy is the total energy, so potential energy of Q Q, potential energy of the slider at Q should be less than the potential energy of the slider at P. Hence, Q can be located below P. That is the conclusion we can arrive from this. Okay, the main thing we have to concentrate is the radius of curvature, where in this case of ellipse it's smaller. Okay, question number 3. A semicircular rigid cylindrical tube is placed on a horizontal floor. Two identical balls that loosely fit inside the tube are simultaneously released from the top of the tube. Each ball moves down the tube on either side. Which of the following statements best describe the total force of normal reaction between the tube and the floor? Okay, first I have to tell you this concept. This concept is nothing but you take a surface and then a hemispherical dome over here, and let's suppose we have a ball here and we are just pushing a ball. Okay, it's unbalanced. Okay, just we are pushing it with a very minimal force so that it moves. It's here its velocity is 0, it has only potential energy. Okay, now when it reaches a particular angle, okay, assume this is not rolling. Okay, now this angle is theta, mg is over here. Okay, mg cos theta acts over here and normal reaction acts here. Okay, now what happens is mg cos theta minus n is nothing but centripetal force. Okay, that is force acting towards center, which is mv square by r. Now by conservation of energy, gain in kinetic energy is nothing but loss in potential energy. There is no other energy involved here. So half mv square is equal to mg r into 1 minus cos theta. Okay, this is, let's suppose this is r, this is r cos theta, and this is r. So change in potential energy is mg r into 1 minus cos theta. Okay, now from this what I can get is mv square by r is nothing but 2mg into 1 minus cos theta. Okay, now if I substitute this here, at some particular point this will leave the contact with this dome, right? So at that particular time normal reaction would be 0. So mg cos theta would become 2mg into 1 minus cos theta at that particular point during leaving. When it leaves the contact, I'm speaking. Okay, now mg gets cancelled and cos theta is equal to 2 minus 2 cos theta, from which I can say 3 cos theta equal to 2 and cos theta is equal to 2 by 3. When cos theta equal to 2 by 3, this leaves the contact with the bottom one. After cos theta equal to 2 by 3, it touches the top one. Okay, when it is in contact with the bottom one, the force on the cylindrical tube would be downwards. Okay, the force on the cylindrical tube would be downwards. So the normal reaction would be initially high. That is initial normal reaction between floor and tube will be high. Okay, since both the forces are initially in this direction and it keep on moves till theta equal to cos inverse 2 by 3, it would be in this direction. So some component of this will only act in vertical direction, so it would decrease. Okay, and it would decrease, and at cos theta equal to 2 by 3 there is no normal reaction. Okay, at theta equal to cos inverse 2 by 3 there is no normal reaction, so it occurs a minimum, and then what happens is it increases. Then what happens? This come in contact with the topmost points, and the force would be like this. Force acting would be like this, and then it will try to lift the tube from the ground. This normal reactions would try to lift the tube from the ground. So option C and D are the correct answers. Question number 4. One end of an elastic cord is attached to a block of mass m, and the other end is held, keeping the cord relaxed and vertical. Relaxed length of the cord is L, and there is a mark P at a height 0.8 L from the lower end. If the upper end is slowly raised, the block leaves the ground. When the mark P reaches the point where upper end of the relaxed cord initially was, the expression for the work done by the force applied by the hand is. Now, if you see, let's mark the initial positions first. We draw, this is the initial one, and I am drawing some bit, not, this is the initial chord, and point P is about here. This distance is 0.8 L, and this is the reference point at which our hand is there. And after applying some amount of force, what we get is it just got lifted. Okay, this is a very small quantity which is approximately 0. Consider. Now it goes about this distance, and point P comes here, which is point P goes 0.2 L, it covers 0.2 L distance. Okay, now where would this stop reach? We have to find it out. Okay, but because we are applying force F here and it is here. Okay, now 0.8 L goes to 1 L, correct? It is uniformly expanded, correct? So 1 L will go how much? That we have to find. Okay, so it's nothing but 1 L will go 5 by 4 L. Okay, so the total extension is nothing but L by 4. Now, since this is an elastic cord and we have to find the work done, right? So work done is nothing but, the total work done is, we are doing 0 work in lifting this block. Let's write work done to lift the block plus work done in extension of this particular cord. Okay, let me write it completely. Work done to extend cord. Okay, now this cord can be assumed as a spring. Okay, this cord can be assumed as a spring. Okay, now you let me introduce this notation. Y is equal to F by A into delta X over L. So this would give F is equal to YA by L into delta X, correct? Now this is similar to K into delta X. F is K into delta X. So YA by L is nothing but the spring constant. Okay, so net work done is nothing but half kx square, that is change in potential energy of the spring. We are using the string to spring analogy, so YA by L, okay, into delta X is nothing but L by 4. Now another thing we have to think about is, what is the force F? Actually, this is, we have to assume this is a very thin and it is a massless, so force F, it has no normal reaction, so force F at this particular point is nothing but mg itself. Okay, so mg is equal to, this is whole square, half, this is nothing but half kx square. Okay, where x is the extension. mg is nothing but ya by L into L by 4. So work done is nothing but mg by 2 into L by 4, which is mg L by 8. Here we have to be clear. At first students will be confused whether to consider the work done by block or what, this ka work done and this work done. Okay, students will be confused which work done should we take. Here we have to assume that the work done here should is 0 because there is no a valuable amount of displacement, so total work done is 0 here, and here there is an extension, and students get confused how should we calculate work done or when we extend a string. So we have to apply string to spring analogy at that particular position or at that particular places. Okay, our next question is also a similar kind of question. You can practice this analogy and think about it. Question number 5. A ball of mass m is suspended from the ceiling with the help of an elastic cord. An additional downward force applied on the ball, if increased gradually to a value f0, the cord would break. What should be the additional minimum constant force F that will break the cord? Okay, let me draw the situation out here. Let this be the cord and we are attaching a ball of mass m. Not perfected drawing, but still. Ball of mass m. Now this acts at tension T, and if we apply F0 force and mg here out here, this breaks. Now let's assume this is an elastic cord, so this cord can be assumed as a spring, okay, which breaks if we apply f0 plus mg. Okay, so we consider it, since it is elastic, I'm just considering this case. F0 force is applied, mg is applied. Okay, now the counter force would be kx. So k is the spring constant, kx max, this is the maximum extension of the spring possible. If we go beyond it, the spring would break, which is equal to f0 plus mg. This is one of our equations. And now okay, now we are going to add, we have to go find the minimum force F for which it will break. Now if we are applying, here comes mg. Okay, now at some particular extent we get kx is nothing but, at this particular instant, if f is less than f0, suppose kx would be the counter force. What is kx? F plus mg, right? Now about this point, now let's take this. Okay, about this point, since a spring is already extended, okay, let's consider a spring is somewhat extended and the current equilibrium position is this. Okay, now it will oscillate about this equilibrium position, right? Its amplitude would be, amplitude is nothing but the applied force F by K, correct? So the amplitude is nothing but F by K, and let's first write x is equal to F plus mg by K. Okay, and from this equation I would write x max is nothing but f0 plus mg whole divided by K. Now from the initial position, let's suppose the spring extended, this distance is x, the equilibrium is x distance apart from the initial non-elongated position. Okay, so uh, from this, if this oscillates till this distance, that is amplitude, we get x plus a, which is 2f by k plus mg by k. which is the extension, this should be less than x max, else the spring would break. Correct? Let's consider at which force F this would break. At that particular point, both would be equal, right? Which x plus a should be x max, right? So I'm just equating this to, and what I guess is mg by k gets cancelled, and f naught is equal to 2f, from which I can conclude the f is nothing but f naught by 2. Okay, so the additional minimum constant force, this f naught is actually we are increasing. Okay, so it would not oscillate at this point, and here we are just applying a constant force, so about this point it would oscillate. So f is equal to f naught by 2 is the correct answer.